Okay, this video is on infinite geometric series, and we're going to start with an example that we've seen before. A patient is given a 20 milligram injection of a therapeutic drug. Each day the patient's body metabolizes 50% of the drug present, so that after 1 day only 1/2 of the original amount remains, after 2 days only 1/4 remains, and so on. The patient is given a 20 milligram injection of the drug every day at the same time. And part A says write a geometric series that gives the drug level in this patient's body right after the nth injection. So let's take a look at this. So right after the first injection, there will be 20 milligrams of the drug in the patient's body. After the second injection, that will be on the second day, this amount that was injected the first day, that's going to become only 1/2 of what it was before. So that's going to be 20 times 1/2. And then we need another 20 to add on. That's the 20 milligram injection for the second day. On the third day, again, we get another 20 milligram injection. And then all of this that was in the body on the second day, this is all going to be reduced by 1/2. So 20 times 1/2. And this amount here is also going to be reduced by 1/2. So we got 20 times 1/2 times 1/2, or 20 times 1/2 squared. On the fourth day, we again get another 20 milligram injection, and all of this, which was in the body at the beginning of the third day, that's all going to be reduced again by 1/2. So this amount here is going to be multiplied by 1/2. This amount here is going to be multiplied by 1/2. So 20 times 1/2 times another 1/2, so that makes that squared. And then this amount here, 20 times 1/2 squared times another 1/2, so that makes this to the third power. And once again, we see this kind of familiar pattern. If we want to express the amount of drug in the body after n injections, it's just going to look like this, and our last term is going to be this times 1/2 to the 1 less power. That is 1 power less than this value here of n. So this would look like 20 plus 20 times 1/2 plus 20 times 1/2 squared plus 20 times 1/2 to the third plus, and again down to 20 times 1/2 to the n minus 1 power. All right. So there's our geometric series. And I notice that this is a geometric series that has A, our first term, is 20, and R, our common ratio, is 1/2. So part B says write this series using sigma notation. Okay, well I know how to write it using sigma notation. This is going to be the sum I going from 0 to n, because I'm going to have n terms. And my term here that I'm going to keep adding to itself is just going to be 20 times my common ratio, which is 1/2, to the variable I. So this sigma notation, if I were to expand this out, I would start with I equals 0. That would give me 20 times 1/2 to the 0 power, which is 1. So that would be my 0th term. And then I'd let I equal to 1, and that would give me 20 times 1/2 to the first power, and then I'd get 20 times 1/2 to the second power, and so on. So this is my series expressed using sigma notation. Part C says write the explicit formula for this geometric series. Well, once again, I already know how to do this, because since I know that my value for A, I know what my first term is, and I know what my ratio is, and I know that the formula for the sum of a geometric series is A sub 1 times 1 minus r to the n over 1 minus r. Then I just need to plug in my values for A sub 1 and r. So A sub 1, that's my 20 milligrams. 1 minus, let's see, r is 1/2. So you say 1/2 to the power of n over 1 minus 1/2. And there's my explicit formula for this geometric series. Now the next part, part D, it says, suppose this patient receives injections over a long period of time, what will happen to the drug level in the patient's body? Well, let's say that the patient receives 10 injections, and I want to know what's going to be the level of the drug after the 10th injection. And I'm just using Q here to stand for the level of the drug. Well, I already have this formula here for the level of the drug after N injections. So if I want to know how much drug is in the patient's body after 10 injections, I just need to plug in 10 for N and evaluate my formula. So that's going to be 20 times 1 minus 1/2 to the 10th power divided by 1 minus 1/2. And I'm going to evaluate this part here in the parentheses. 20 times, if I evaluate this with my calculator, 1 minus 1/2 to the power of 10, I get a number that looks something like 0.999023 over 1 minus 1/2 is 1/2. And then if I keep going and punch that out into my calculator, then I get 39.9609375. All right. How about if I want to know how much drug is in the body after the 15th injection? Again, I'm going to use this same formula. I'm just going to replace my N with 15. And let's see, that's going to give me 20 times, and again, if I evaluate this part here in the parentheses, I get 0.99996948 over 1/2. And if I punch that in, then I get 39.9987793. All right, how about if I evaluate it for 25 injections after 25 days? Well, again, all I have to do is replace 25 with my value for N in my formula. So 20 times 1 minus 1/2 to the power of 25 over 1 minus 1/2. And again, evaluating this part in the parentheses, I would get 0.679999702 over 1/2, and that's going to be 39.9999981. All right, well, it's not too hard to see what's happening here. It looks like the more injections this patient receives, that is, he receives 1 injection each day, and as the injections go on and on and on, and I keep adding up the amount of the drug left in the patient's body, it looks like it's getting closer and closer to about 40. It's getting closer and closer to the value 40. Well, it's not too hard to see why that is, because notice that this number here, that is this number we evaluate in the parentheses, this number keeps getting closer and closer to the number 1, which means that this whole formula, it looks like it's becoming closer and closer to 20 times 1 minus, this number here just keeps getting really, really, really small, and it's not hard to see why. 1/2 to the power of 25 just means 1/2 times 1/2 times 1/2. Every time I multiply this times another 1/2, it just keeps getting smaller and smaller. And if I let this number keep getting bigger and bigger, this exponent here, well, this number just essentially becomes approximately 0. So I've got 20 times 1 minus 0 over 1 minus 1/2. And this becomes 20 times 1 divided by 1/2, which is 40. So the larger this number gets, in other words, if I say let n begin to approach infinity, then this formula essentially becomes this formula. And the amount of drug in the body begins to level out at 40. Well, what we have here is something called the sum of an infinite geometric series. And as we've seen, as the number of terms in the series approaches infinity, if the sum approaches a finite number, in this case our sum approached 40, if the sum approaches a finite number, we say the series converges. Notice this can only happen if r, that is our common ratio, is less than 1, or more specifically, if the absolute value of r is less than 1. If the absolute value of r is less than 1, that is if our common ratio is less than 1, and in this case it was 1/2. If the absolute value of r is less than 1, then we can write a formula for this sum. And our formula, that is the formula for the infinite sum, the sum of an infinite number of geometric terms, you say as n approaches infinity, that formula just becomes that formula that we saw before, which is a, our a sub 1 number, over 1 minus r. So in this case we had a was 20 over 1 minus 1/2, and that gave us 40. If it turns out that our common ratio is greater than or equal to 1, then we say the series diverges, in which case the sum does not converge to a single number. It just keeps getting larger and larger, so we don't have a formula for that. So let's take a look at this example 2 here. It says, if possible, evaluate the sum of each geometric series. So I can see in each one of these I have an infinite geometric series that is...
Mr. Fushi, please contact the front office. Mr. Fushi, please contact the front office.
That is, I can see that it's got an infinite number of terms, and each one of the terms is in the form of a times r to the power of I. A times r to the power of I. Well, this one, my r value is less than 1, which means I can just use this formula right here. S sub n, as n approaches infinity, is going to be equal to, let's see, a, in this case my a value is 2, over 1 minus my r value, which is 3/4. So that's just going to be 2 divided by 1 minus 3/4 is 1/4. 2 divided by 1/4 equals 8. So the sum of this infinite number of terms is going to be 8. This geometric series, on the other hand, since this value here, my r value, is greater than 1, that means the series diverges. So it's not possible to find a sum.